announcement. So no homework this week. And deadline, in our course, deadline is anyway a very relaxed word. For exercise, Alicia, what is it, exercise 7?
7.
Is, anybody know the day? Not next Friday, but the following Friday. Any guesses?
9.
No, first. Come
It's
on.
second.
Not not tomorrow or next week.
It's
It's,
2nd of
I
November.
think it's second, it could be the second.
yeah, could be.
Okay. Is, I know you have midterms and many things, so it gives you some chance to catch up. So the theme today is structure and operations on bundles. And in particular, vector bundles. Well, the most important thing, Riemannian metrics on vector bundles. And since this is a course where people of who are interested in physics are present, Riemannian metrics and as well as Lorentzian structure. So, first of all, let us recall various operations on vector spaces. So you start with a vector space, and what can you do? One thing you can do is go to the dual space. All of our vector spaces at this stage are finite dimensional, so there are no delicate points. If your vector space is infinite dimensional, it's not so clear what is the good dual space. I just warn you. In infinite dimensional context, it is not so clear what you should really take as the dual space. It is usually some question of topology. Well, another thing is this. So associated to a vector space is the space of linear transformations. Okay? Associated, well, let's say here, to two vector spaces, you have the linear mappings between the two. Associated to one vector space, you have the bilinear mappings, the bilinear forms, so bilinear forms. On V. And as you know, the bilinear forms are the mappings from V to its dual. These are examples of starting with a vector space or starting with two vector spaces, how you derive other very, very relevant vector spaces. The endomorphisms, the linear mappings of V to itself, the maps from V to W, the linear mappings, we call it HOM, an example of bilinear form. Now, all these things can be transformed to the bundle, transferred to the bundle level. So if you have a vector bundle, E over B, and we're all here in mathematics, we talked about this at lunch, a bit about the values of physical type of thought. Physics thinking frees you up a little bit because nature is so complicated, we don't need to be exact at first, we just have to have some idea what we might be able to do. So what we might be able to do with, you start with some bundle, vector bundle, so this is a vector bundle. It might be very logical to go to a dual bundle. That was the first thing we did here. Why is that logical? Why is that logical? Well, here's the vector bundle, and each fiber is a vector space. This is the vector bundle E over B. Here's the base, here's pi. Each fiber is a vector space, that's a vector space. Well, we can make just the same bundle over here, but instead of a vector space, the vector space being a fiber over some base point B, like this is the vector space E, the fiber over B. Why not just take the dual space? This makes sense. We replace every fiber, which is a vector space, by its dual space. Okay, that's very formal, in a very formal sense, a dual bundle. Let's try some more experiments. Let's look at B. Let's look at the endomorphism bundle. So we have a vector bundle E over B. And well, let's just replace every fiber by the endomorphism. That means if I have here a base point B, and I have the usual bundle upstairs, and I have in this fiber here EB, then I just replace this whole situation here, same base, but we exchange, instead of having the fiber, the vector space, we have the endomorphisms of that vector space for every B. For every B, we have a fiber, we have its vector space, we have the endomorphisms. Fibers here, we have the endomorphisms. Of course, this is a bundle of rank, let's say, R, the fiber dimension is R. Then this rank over here will be R squared, because these are effectively, as you understand, in the basis matrices. Okay, that's, what else can we do here while we're having fun? Well, why not? Let's start with E over B. And let's go to the bilinear forms over B. Why not? We have the fiber EB is replaced by the bilinear forms on EB. Well, that's not so difficult. We replace the fibers by the maps from EB to the dual space. We know how that is. And this is the idea. You start with one vector bundle, one vector space, and you have all these operations you can make here, and you get what we call associated bundles. You have associated bundles, and this is a completely formal thing until you are a little bit careful. Because here we were just talking about some formal replacement, so let's be a little bit careful. Be careful with many things. I would say one, structure group. Two, the action of the structure group on the fiber. Well, the fiber. And three, the action of the structure group on the fiber. On the fiber. And of course, all of these things are tied closely together with the smoothness, because we need smooth local trivialization. So, let's have some fun with structure groups. So, the structure group for structure group for the dual bundle. Well, if G is GL and R on the original fiber, which is a vector space, Rn, then the new structure group is the same, GLNR on Rn, but let's emphasize dual, because you've gone to the dual space. Okay? So, if we have G, a linear transformation on Rn, so in GL and R, then G of a function, so this function is in R is in the dual space, so Rn star. Is everybody here sure he knows what G of a function is F composed with G inverse. So this is how you take G of a function. You understand what I'm saying? Yeah. So the G of F at a vector V is equal to F of G inverse of V. You understand why the inverse? Yeah, because if, well, let me just write it to be sure you understand. The inverse is there because what? G H of F is the same thing then as G of H of F. Right? If you did not put an inverse there, this would reverse here and would not be a representation that way. Okay, so this is the dual representation. If you have the standard representation of GLN on Rn, then this is the standard way to dualize it on the dual space. And this is then the structure group action. The structure group is the same group, G, Ln, but it acts in this dual way on the dual space. Okay. That was the structure group in the case of the dual bundle. Let's talk about what were the other points? Fiber. Well, the fiber was Rn star. The action. Well, I've answered all questions. The action of the structure group I've told you. And so, yeah, again, the structure group is still GLN. It's just acting in a different way on the dual space. The action of the structure group I just told you about. What we need is a smooth local trivialization. So, if phi alpha u alpha Rn into E restricted to U alpha is, suppose this is the local trivialization, a trivialization of the bundle E. Well, E restricted to U alpha. All right. Then, in some sense, let me just use some funny notation. Let's see, call it phi star of U alpha, the trivialization of the dual bundle. I have to tell you what that is. You just have to take the dual frame. So here you're taking the standard basis E1 through En as a frame. Here you take the dual frame. Okay. So here you have the standard frame. Standard frame E1 through En. Here, and here you have the dual frame. F1 through Fn. Okay? And now change of frames is going to be different. All right? If change of frames in E is given by G alpha beta, and now you're going to hate me because I'm going to put upper index down to lower. Let me tell you why. When I introduced G alpha betas before, I had some index. I don't know why. I put the alpha beta upstairs. Now I'm going to put other notation upstairs. So I would like to put the alpha beta downstairs. Okay. So this is the transition matrices for on the intersection. These are matrix valued transformations, of course. Now, what was your point, Elisa? Some people were confused about the.
They thought they had a composition when you multiply G alpha beta times G beta, not a multiplication of functions pointwise, but composition.
It's composition of operators.
Well, I mean, it's pointwise multiplication.
Of matrices.
Of matrices, exactly.
Yes, which is composition of operators.
Okay, yeah, but they thought something different. They thought it was composition of functions.
Oh, no, it's composition of the mappings.
Yeah.
Composition of the mappings, which corresponds.
I mean, if the composition of actually doesn't make sense.
Of course, it makes sense.
At each point is a composition of the matrices.
So we're talking. This is probably worth talking about. So we had a co-cycle condition here. If I get it right, there's some challenge. Yeah. Okay, here's an example of a co-cycle condition. Now, we're discussing what this means here, right? Okay. Now, these are in GLNR. So what does that mean they're in GLNR? It means they're mappings from U alpha beta to GLNR. That means a point X, let me emphasize, a point X gets mapped to G alpha beta of X. Okay? If you like, that's a matrix. So this product here is matrix product. Okay? It's also a composition of operators.
No, I mean, if it's composition of operators, you just, for example, take the argument of X, then you will have, for example, G beta alpha, G beta gamma, all like composed with an operator, which this is not defined. Because G gamma alpha is in GLN.
I don't know. If I have a vector space V1 and a vector space V2 and a vector space V3, and I have S and I have T here, right? Then I have T composed with S. Nobody debates this, right?
The point here is T is also from V1 to V2.
What?
In this case, the T, which is G alpha beta, for example, is also from V1 to V2.
Yes. So let me write it down here. You have so we have Rn, let's G alpha beta, let's put all notation of x, Rn, G beta gamma of x, and Rn. Okay? Now what? I'm talking about this operator here. What's the question?
No, my question is, they are not composition of G alpha beta, G beta gamma. I mean, these
Well,
are.
that's how we define multiplication of matrices is composition of operators.
Yes.
And this is what multiplication
Well,
is.
Alexandros perhaps can clear this up.
Yeah, okay, I was also confused by this. Okay, we want to say that the composition of G of X, of the images of some points, like G alpha beta of X with G beta gamma of X, not the composition of G alpha beta with G beta gamma.
Is that the confusing point?
Yeah.
Okay, so what I'm talking about, I'm sorry, it's probably, the way I've got this set up, it's terrible with indices, so, but you know what I mean. So first we have to do this thing, and then this thing. So, no, it's okay. No, it's wrong. From the point of view of indices, it's wrong now, but that's not important. This is this. Are you happy with that?
Yeah, I know.
What words you happy with? And that, if you write down the matrices just means you multiply the two matrices. What's the problem?
No problem for me. I just want.
No, they thought something different. Here we evaluate both alpha beta and beta gamma at x. And they thought we first apply G alpha beta to x, and then we apply G beta gamma to the result of G alpha beta of x. I mean, like composition of the mappings from you.
Oh, I see. No, it was a question, I see. So it was a question of where these parentheses are in here someplace.
Yeah.
Okay, but now it's clear what it's
Yeah,
meant.
no, it's
Okay. But it's good to clear these things up. Sometimes formal points are confusing. Okay, thank you. Okay, so before I made the sidetrack, this is the way this is the frame change for the bundle E. And the frame change for the bundle, and that's a matrix. It's a matrix valued mapping. And the frame change for E dual is, if you write it down, G alpha beta transpose inverse. Okay? And do you understand why that is? Let's make sure we're on the same track on this, okay? Yeah? What we're using here the standard identification that this is x of y. And x of y, this is the standard inner product, x of y is x of y is a function, is considered here a function of the argument y. Okay? And what we will get here is then g of this, so this is a function, let's write this, this is a function of y. Okay? And g of f is equal f of g inverse. And that means that what happens, g of this function is of y is this function at g inverse of y, right? which equals G inverse transpose of X applied to Y. Okay? So you see, this is the action on matrices. Okay? And let me just comment, this is perhaps a confusing point, you maybe need to think about it a little, it's completely trivial, but you need to think about it a little bit. X, this is, just keep in mind, is X transpose times Y. Right? So you see, X of a matrix times Y is X transpose of A of Y, which is the same thing as A transpose of X transpose Y. Okay, and we put an inverse here because we need to make it an action. Okay, and you see this transformation, A goes to A transpose inverse. It looks crazy, but don't forget, if you just do transpose, you mess it up. A times B transpose is B transpose A transpose. Right? So you must have this minus sign here to make it a representation, namely to make it really an action. If you have minus transpose here, this is exactly what it's supposed to be. And you can check everything I say here in coordinates, anything you want to do, and check to see that for if E is given by G alpha beta, then E star is given by G alpha beta minus transpose. Just keep that in mind. Okay. And therefore, if E is a smooth vector bundle, it's completely obvious that E star is a smooth vector bundle, because what we did to go from here to here is one of the smoothest operations I know. Inverse transpose. It's a little bit complicated because of inverse. Right? The inverse of a matrix is a non-trivial operation, I think. But it's inverse transpose going from here to here. So this is going from E to E star. Okay? That's the dual bundle.
Professor, more precisely here, the G alpha beta inverse transpose should be the inverse transpose of G alpha beta applying to some argument, for example, X, because it only applies for the linear map.
Sure. We're talking about the fiber being Rn, and I told you the fiber is Rn. And now I'm telling you how the co-cycle, the transition matrices operate on Rn. X goes to G alpha beta inverse transpose of X, or times X as a column vector. Okay? Is that okay?
Yeah, because I just want to make it clear that the inverse transpose is applying to G alpha beta of X, because it doesn't make sense.
I see. Yeah. It's a very good. Again, a sloppy notational point. You see, you Chinese guys have this incredibly complicated kanji. Do you call it kanji? No, probably that's Japanese. These symbols, and therefore they watch symbols very carefully. You know. I have these trivial symbols in my head, so I don't watch symbols. So, no, really, I understand your point. I understand your point. Okay. So what we're talking about is G alpha beta of X. Just to make sure we understand, X is in U alpha beta and is mapped by this transition to this matrix. Okay? That's your point. And it was my bad choice of notation. And now for vector in Rn, which we think of as a column vector, it's exactly your point. We have G alpha beta of x applied to this vector by matrix multiplication, if you want. That's what you were saying, I think, right? Okay? And G alpha beta transpose inverse of x is also a matrix, is also a matrix, and the confusing point is it's not just, yeah, it's clear. If we start talking about it too much, we're confused. Okay? It's clear what that means. Actually, maybe I see your point. Maybe I should write it here. Now, no, really, it's true. I should write it there. Now you're satisfied, right? Yeah. Thank you. Okay. That's that. Okay. Let's start with E, and let's go to the endomorphism. Okay. So the fiber here, the fiber here was Rn, and here the fiber is the endomorphisms on Rn. Here is a vector bundle, so for A in GLN, R, and V, a column vector in Rn, then V gets mapped to A times this column vector. And here for an endomorphism, I don't know, B, an endomorphism, right? The associated mapping is B gets mapped to A, B, A inverse. Right? So if the change of basis goes by matrix A, then the change of the endomorphism goes by A, B, A inverse. Okay? Good. So this is now, even still the structure group is here GLN, the structure group is still GLN. And of course, this operation, if I have an operation of GLN on Rn, this operation is also smooth, so we have a smooth bundle. Okay, let's talk about something more interesting, bilinear forms. Okay. So, I needed to tell you what so you start with E, and F is the fiber Rn. I'm boring you to death. If you take a vector in Rn and a matrix in GLN R in the structure group, then V gets mapped to A times V. That tells you everything. If I go to the bilinear forms here, E, the fiber now is the bilinear forms on Rn. And if I take B here, bilinear form, and I take A matrix, I have to ask how it acts on bilinear forms, because this is going to tell me what the structure of this bundle is. Well, let me see here. It's A of B of V W. Guess what? B of A inverse W. Right? It has to be because we're dealing with functions, and you have to move the inverse inside because it needs to be a left action. So this is the correct action on bilinear forms. Let's see here. The bilinear forms on Rn are just matrices. Right? In an obvious identification, namely bilinear form xy defined by the matrix M is just x transpose my, right? We use the standard scalar product to write these things as matrices. Right? Every bilinear form can be written that way. I didn't say symmetric. Okay, so this is any bilinear form, so it's any matrix. Okay? So this is this is the bilinear form Bm, defined above. So let's see what G of Bm is. G of Bm applied to xy is equal, now I have to put, let's say G is a matrix in GLM, so I can write it as a matrix. So A of Bm, I have to put it inside, so that's Bm of A inverse x, A inverse y. Now I have to see what that is. This is a terrible thing. This is A inverse transpose M. It's X transpose A inverse transpose M A inverse of Y. So the matrix, the action on bilinear forms in this realization is M goes to A inverse transpose M A inverse. This is the rule. And that is as smooth as it gets, because inverse is smooth operation, transverse is smooth operation. It's about. Now, this is really horrible, but it's necessary to have here on the left inverse transpose, because inverse transpose works well. Inverse transpose of AB is AB. Inverse transpose of A, inverse transpose of B, and the same thing here on the right. So you must have inverse here on the right and inverse transpose here on the left. You understand? This makes this a homomorphism, right? You act by A and then act by B. It's the same thing as acting by A, B. Okay? Well, that's a little bit boring, but I think you see that all sorts of different things appear from one vector bundle in a very elementary way. Now, enough of this formal business today. Let's have some fun. I want to talk about Riemannian metrics. So the next topic, and probably the only remaining topic, for today, is the topic of Riemannian bundle metrics. Riemannian bundle metrics. Well, whenever you think of bundles, just start thinking of the first step is at the vector space level. let's take a vector space, finite dimensions, and B, a bilinear form, and this should define a geometry, this should define Euclidean geometry. So bilinear form defines a Euclidean geometry on B. If and only if you like, this is a definition. If and only if is symmetric. And positive diamond. Symmetric is clear what it means. Well, I hope both are clear. So B of BW is equal to B of WB. And BB, the norm, which I will always call the B norm of V squared, is positive for V not 0. As you know from your elementary classes, this defines a standard distance function, and this distance function will have Euclidean properties. Okay. That's what's going on in the vector space. So, if you have a vector bundle, here, a vector bundle, here's V, here's EB, and on EB, we might want to have, oh, EB, oh, there's so many B's here, it's just terrible. B is a base point, and B is a bilinear form. Now, there's some language here where you have different letters for those things. What is it in Uzbekistan language? Base? Base or something?
We use from Russian.
Russian, what is it in Russian?
Basis.
Huh?
Basis.
Basis. Okay, any other choices? For bilinear form. F for a form. How about that? Okay, and let's say F a bilinear form. Oh, F is the fiber.
You take E of X.
Yeah, exactly. I'm glad somebody came up with a sensible solution. The base point will no longer be called B, it will be called X. Okay? And on this fiber, I would like to have a bilinear form, B of X. And that means here on this fiber, I have geometry. On the fiber over here, I would like to have geometry also. Fiber EY, I would like to have a bilinear form BY. Okay? Now, it is completely clear, unless you're out of your mind, that this bilinear form should vary in some reasonable, vary in some reason. Here's a bilinear form, and all nearby forms are just completely different. There's no that would be terrible. Come on. The world is not that bad. So, at least generically, it's not that bad. So what we need is smooth variation of Vx as a function of x. Right? Smooth variation as a function of x. Now the wonderful thing is, we don't have to think. That's always nice, we don't have to think. Because what I do is, I say, look, hey guys, here's the bilinear form bundle. Here's the base. Here's the projection. And the bilinear form is a section of this bundle. A smooth section of this bundle. Remember, a section maps the base into a section like this. We've talked about it at least in the homework. Yes. And to every point x, I get a bilinear form Bx, and a smooth section is a very is a smooth bilinear form on the bundle. Okay. So a bilinear form on a bundle, a smooth bilinear form on a bundle is a section of the bilinear form bundle. So smooth bilinear form B on the bundle E, on the vector bundle E, is a smooth section of the bilinear form bundle. At every point, you have a bilinear form on that fiber. B sub of x is a bilinear form on the fiber over x, and as we move, the bilinear form moves smoothly. Okay? Just another formulation of smooth movement of the bilinear form. Okay. Well, the first property is symmetric. This, I claim, is a good property. Why? Because if you take one symmetric bilinear form and add it to a second, space of bilinear forms is a vector space, right? I mean, you just add two bilinear forms and multiply and so on. If you take one symmetric bilinear form and another, you add them and they're still symmetric, right? You multiply by a number, it's still symmetric. This is great. This means that this is a vector bundle. Let me write it. Sim bilinear form is a vector bundle over the base. Right? Right? If you like, it's a subbundle of the bilinear forms, because the symmetric bilinear form, a symmetric bilinear form in a vector space is a subspace of all the bilinear forms. Okay? So a symmetric bilinear form is just a section here. Section is another way of saying to every point you have a bilinear form, in this case symmetric, and it moves smoothly. So symmetric is no problem. But now we get to something that's really very non-trivial, and that is the condition of positive definite. I always like to draw pictures. They help me immensely. So let's try to draw a picture of the space of positive definite symmetric bilinear forms. Okay. Now this is going to be a vector space over the point x. Thank you for your help. X is the point of the base. Use the 0. 0 is always well defined. This is going to be the symmetric bilinear forms on the fiber over the point x. Now, do you have any suggestions how I should draw the positive definite symmetric bilinear form? If I add two positive definite symmetric bilinear forms, is it still positive definite? I hope so. Yeah? Right? Well, the condition B1 of VV plus B2 of VV is always positive. Come on, that's no problem, right? So I can add. Any other operations you like? Yeah?
You can definitely multiply by a scalar because it will come out in front as a square.
Positive.
That's inside. I'm-
Okay, outside, positive.
Yeah, positive scalar outside, right? Positive scalar outside. What about linear combination? AB1 plus BB, oh, okay, here we go again. C1B1 plus C2B2. What?
It's also positive, definitely.
Well, it depends on C1 and C2.
Should you draw the cone of light?
C1 is equal to C2.
Yeah, it better, so it's a convex cone, right? We're talking here about a convex cone, right?
Yes.
So you can take, I never write convexity like that. I write as T B1 plus 1 minus T B2 and then take the homotopy somehow as T runs from 0 to 1. So that's a segment, that's what you're talking about between. So this is then a convex cone. So it looks something like this. This would be the positive definite bilinear form. This is a positive definite bilinear form, a symmetric bilinear form on the fiber over X. Now, I hope you're starting to get a feel for the picture. If I do something over here, over another point, X hat, here again is the same picture that we just discussed. In that fiber you have the notion of linearity, so you have the notion of convexity, and here, this notion is well defined, this positive cone. And if you have it at another place, over here, the notion will still be, here will be 0 again, here will be 0. 0 is well defined. 0 bilinear form is 0, 0, 0, I know what that is. Here we have this positive cone in every fiber. This is the positive cone over X. This is the positive cone over X hat. Here's the cone over, I don't know what we have down here, say Y. I don't care. Okay? Now, first question, and this is a question really that stems from Riemann's basic work when he was your age, is whether or not these things exist. Do there exist positive definite bilinear forms on a manifold? It's a reasonable question, right? You see why it's reasonable? It is reasonable because what it is, positive definite bilinear form is a section B which lands in this positive cone always. You get it? It must land, it's a section that must land in this cone bundle. Now if you just take a section of some bundle, which you could probably make, how do you know it's going to land in this cone bundle? That's really a non-trivial condition. Okay? So the question is, does such a thing exist? Is there a section in this cone bundle? The answer is yes, but because of positive definiteness. If, and that was my theme for today, if you go to relativity theory where you do not have positive definiteness, I will talk about this in a minute, sometimes you may not have such a geometry. In fact, very seldom do you have a geometry. I will repeat that at the time. We do have these exist. So such Riemann, we call this thing, if it exists, a Riemannian bundle metric. Exists. In fact, there are many of them. I hope you understand how to make many. If you have one, how do you make it? How do you make many? Just introduce small earthquake, right? You see it lands in this open cone bundle, so if you make small earthquake anything nearby is still going to be positive, definite, symmetric, and everything, right? Okay, so it exists. So, construction. This construction now is a method that I will take 5 minutes to explain. You already know this construction. So step one on the construction, take a double cover. Of the base manifold M. So let's call this base manifold M. We have a vector bundle given over the base manifold M, and we're trying to construct a Riemannian bundle metric on that thing. By the way, I've dealt with many friends all my life in mathematics. One was the great differential geometer Yozo Matsushima, who told me in Japanese, "Oh, many bundle metric. Question is, which is good metric?" Yeah? This is the question. Maybe one good metric, other metrics no good. Yes, this is a statement. Yes, there are many metrics. That's just some mathematical statement, but a good metric, for example, satisfying curvature conditions and so on, is important. So anyway, take a double cover of M. Call this U alpha finer than V alpha. So this means that inside V alpha you have U alpha, and I take U alpha, of course, to be compact in V alpha. So I'm having to use this word compact again, but we talked about what it means. It means it's bounded inside of V alpha. And you have such double coverings. That is a fact that you should check. If you haven't checked this yet, do it. Any manifold has a double covering. The smaller thing is really compact than the bigger thing, but it's a double cover. You understand? The smaller things cover and the bigger things cover. Okay? Well, that's pretty clear how you make that. You start with the smaller things and you expand to the bigger. Right? And then you got it. Okay? But I want these things to be local trivializations by domains over which and this bundle is trivial. Okay? Well, the bilinear forms over there, here's V alpha. Here's this cone. This is trivial. Come on, give me a break. Everything's trivial here. I can tell my wife about this. And ask her how to get a section inside that cone bundle if it's trivial. How do you get a section inside a trivial cone bundle? Well, it's not very hard. You enter from the left, stay in it, and you enter from the right. Well, that's the first thing. Now, by the way, when I write this thing, I mean locally finite. Okay? That means you don't have infinitely many of these things intersecting at once. I mean, you can arrange that. Okay. So we have this section, let's call it B alpha. This bilinear form over V alpha. And I take chi alpha times B alpha. Okay. Again, chi in my case is always a cutoff function. So my wife had the good idea of this trivial bundle, but I cut my wife off just like a telephone pole. So I cut her off. So what we're doing is this. But now we can extend this forever. So this thing is, of course, not positive definite, but at least I did well on U alpha. On U alpha, this thing is positive definite. Okay? Now there's a headline here, a partition of unity. I really don't need to do this here. All I'm going to do here is add these up. That looks insane, but the covering is locally finite. So I'm only adding, what that means where these things are non-zero, there are only finite many sections non-zero, right? And so I'm just adding finite things together. So this thing is really defined, right? And this thing is, because you see here, I didn't do much. I didn't do anything at all here, to my wife's bilinear form. Of course, when I add things with overlaps and so on, I'm going to make something mysterious, but I'm adding positive definite bilinear forms to positive definite bilinear forms, and I get positive definite. Now, guess what? If you have forms that are not positive definite, you may have some negative norms added to positive norms, and you're in big trouble.
Professor, what is this addition, like sum over? Is it sum over?
All alpha.
Okay.
That's what I just said. If I give you a point, this is going to be in only finitely many of these U alphas, or V alphas, right? So the sum is only going to be, it's really going to be finite always, okay? I mean, it looks infinite, but it's not. Okay, so this is a positive definite. So the second point is the cutoff. And if you want an interesting function, is the so-called partition of unity, which is we define gamma alpha to be the sum of the key alpha divided, to be key alpha divided by the sum of the key alphas. And now the sum of the gamma alpha is, of course, 1. So we've arranged what is called a partition of unity here. Quite often, we use this partition of unity, but here you really just need the cutoff. That's a Riemannian bundle metric. And this Riemannian metric on bundles, if it's on a tangent bundle, is called the Riemannian manifold, a Riemannian metric of the manifold.
Professor,
I'm listening, yeah.
Could you give me the definition of Riemannian bundle metric? Because we're constructing something, but I don't know what we are constructing.
Okay. So let's. I think I wrote it, but I'll say it again. A Riemannian bundle metric is a section of the cone bundle of positive, definite, symmetric, bilinear forms on the given bundle.
Well, why is a metric?
Because on each fiber, it defines a bilinear form, right, which is positive, definite, and symmetric. This defines a distance function, which some people call a metric. I call such a distance function a metric. Okay. So for our class, even with open doors, okay, a metric, unless it's a Riemannian metric, either on a vector space or on a vector bundle, means positive definite, okay? Riemann at the time was only interested in positive definite structure. Does that answer your question? No?
So not very clear. I mean, for example, the metric for vector spaces, I can define something. For example, I have two vectors, and between two vectors, there's in some sense some distances. So I call it it's a metric.
Yeah.
But here, what?
But let me tell you, that notion of distance was even in the brain of Euclid in -4000. And in 1850s, there's some Greek guy who would know this. No, that's highly non-trivial. That Euclid understand a huge amount in minus 400 that we didn't go further until Riemann in the middle 1800s. Riemann said the right notion of a metric is not your notion, it is the notion of a positive definite bilinear form that is symmetric. And that's really important for physics. By the way, that's even positive definite bilinear form that's symmetric is too strong. For people who know words, connection is weaker than this, and the correct notion for many things is connection. I will explain. I still don't know. You're getting mixed up with distance function in your brain should be metric. Yeah? Cancel that notion in the area of geometry, particularly nonlinear geometry. Metric is a symmetric, positive definite bilinear form. Obviously, associated to that is a norm function. And associated to the norm function is a distance.
So what you are proving here is that you want to prove the existence of B.
That's right, and I did. Right? So, you understand what I did in this cone bundle. I had, you see, I had many things. These things are points in a cone bundle, these B alphas. So, I had many points here, but only finitely many in the cone bundle that I added up. And of course, when you add them up in the cone bundle, you're getting something in the convex hull somehow, right? I mean, you're getting something in this convex, so I'm still in the cone bundle. Okay? But I use positivity, this is the point, I use positive definiteness very strongly. Okay? Thank you. Well, I will say a few words. Sort of a forecast about what is to come tomorrow. So a Riemannian metric, since you asked me to really write things down more than just saying, a Riemannian metric on a manifold, not on a bundle, is a Riemannian bundle metric on the tangent bundle. Okay. There are many bundles on a manifold. One of them is the tangent bundle. It's very important. I hope you understand what this means. Let's go through it again, because I may have confused with bad didactics. You have some mysterious manifold, and you have a tangent bundle here at a point. This is tangent space. You have two vectors here, v and w, at the tangent space point P. All right? You want to know things about these vectors. You just said you want to know distance. So what you're roughly saying is you only want to know the norm of the length of v, right? I say I want to know a lot more. I want to know angles. Because I want to know Euclidean geometry. Okay? I want to know angles, not just distance. Length. So what we have here is at the point P, I have the bilinear form V, maybe I emphasize V at P, W at P. This gives us angles and lengths, volume. It gives us everything you can think of at that infinitesimal level. And now think how geometry may be changing as you move through space. This is something that took a long time for us to understand in physics. Geometry may be changing as you go through. So the notion of angle and length and volume and all of this may be changing as you go. The change in angles, volume, length, P, and all of these different things is the dependence of the metric on the point P. Okay? This metric is changing with p. Notion of how big is an angle, notion of orthogonal projection, notion of area of a parallelogram, notion of volume of a parallelepiped. This may change. You may, with your eyes, in some physical situation, you may think not, but in fact the metric is changing, and so these notions will be changing. This is fundamental to understand. This is called a Riemannian metric. So next time, we will discuss exactly the same thing, except instead of a Riemannian metric, we will discuss a Lorentzian metric. For example, on a four manifold. When I use four manifold, I mean the dimension of the manifold. Now, the first ideas of Lorentzian geometry came from Lorentz, Dutch mathematician. The Lorentzian metric, the standard Lorentzian metric. So if I write in four variables t, x, y, and z in R4, then the standard Lorentzian metric norm that's how you have to compute a metric. I emphasize here 3, 1 is x squared plus y squared. This is Euclidean norm minus t squared. Okay. We say this is a norm or an inner product. If you don't like this, the inner product of let's say xi eta. Let's say xi is the vector t, x, y, z, and let's make it just let's say xi1 and eta xi2. So ci is ti, xi, yi, zi. This is then minus, so it's then x1, x2, scalar product x, y1, y2, z1, z2, minus t1, t2. Okay? So this is the standard metric of signature 3, 1. Okay? Now, I hope you can see if we take two Lorentzian metrics and add them, you better watch out. Two metrics of signature 3, 1 and add. Can you imagine what might happen? Well, I'll tell you. If one of them looked just like this and had a coefficient here very small, and if another one looked just like this and had a coefficient, you see what I'm saying? With the negative parts can start killing the positive parts if they're big enough. Okay? So the sum of two Lorentzian metrics is not a Lorentzian metric. Fact, and you will see this next time, many manifolds do not have Lorentzian metrics. Relativity theory is very, very special to have such a Lorentzian metric. So let me just close this lecture by writing one down in the language of physics. Not language of physics, notation of physics. It's called the Schwarzschild metric. Sort of the simplest metric where some interesting phenomena arises. And I think reflects something interesting. Okay, now when you read the literature, standard notation is the metric, or Lorentzian metric, whatever it is always called G. I'm guessing for Gauss. And the space, the manifold in this case, is R3 minus a hole, and there's a reason to call this a hole. And the usual normalization for this hole is a ball of radius 2m closure. Okay. This is this times R. This is the time space, and this is the, here the variables will be usually written in some sort of spherical coordinates because this boundary of this thing is a sphere. So is R theta p, and the variable here is t. And the Schwarzschild metric looks like this. G, let's see if I can get it right, is minus, I'm going to write it down in the t first. For some reason physicists always write it down with t first. Now, this is what you guys write down all the time, right? You see that all the time. You stop fooling around with it. You don't know what the devil you're doing. What can this mean? I'm going to count how many letters there are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 44. 41 are 2 letters. This is a metric of signature 3,1 on the tangent bundle of the manifold R3 minus a black hole cross time. Okay? This manifold is, luckily for the audience here, trivially contained in R4. This is good news because the tangent bundle of R4 is trivial. This is obvious because you have you have 4 sections that are independent everywhere. This is easy, this is homework. So the tangent bundle is trivial. So this tangent bundle is trivial of this manifold is nothing more than the manifold cross R4. Until recently, physicists only considered trivial bundles, but they realized in the last half of the 20th century, almost everything in life is a non-trivial bundle in some sense. Okay? But I guarantee you, you will be writing these things, these complicated statements down, at least in trivializations. Okay, what does this mean? Do you understand what this means? This means, do you know what dt means? That means, okay, I'll write it for you. Oh, this might help. This might help. What? 1 minus 2. I promised you 3-1 signature, didn't I? Okay, you understand these kind of coordinates? Everybody's cool with these coordinates? This is a vector in R3. It has polar coordinate radius r. This angle here is theta, and this angle here is phi. Right? These guys calculate like this every day. Okay? That's the coordinates in space. The coordinates here in the linear space are usual coordinates. And now in these coordinates, let's call these coordinates, so the coordinates of r, theta, phi, t. Okay? And now I'm going to write a matrix, R. By the way, look what happens to this thing when you go to the boundary of the black hole. It blows up. You see? What's happening to distance here is going to infinity here. So what is d theta? It's r squared. What is d phi? It's r squared sine theta squared b. And what is t? Minus 1 minus 2m over r. Now you're starting to get what I'm talking about? You see what I mean? I hope, now that I've written this matrix for you, if I give you a vector of A dd r plus b dd theta plus c dd phi plus t plus d ddt. I hope you can compute the length of that vector, can you? It's this symmetric matrix applied to that vector. You understand how to apply symmetric matrix to a vector? X transpose matrix X is what I said. Okay? So if you look at it, well, you can see what it is. Okay.
But why do you have squares in the formula?
What?
Why is it t squared and dr squared and everything is squared?
So, now, it's a good question. What the devil does this d squared mean? I will explain. So d squared, Mihai, you're going to really like this answer. That means dt times dt. Okay. But that means the symmetric form dt tensor dt plus dt tensor dt over 2. The language, by the way, physicists have a very, very compact language. You understand what that means? That means you apply, if I have a symmetric form, fg, that is the symmetric form of function f, g, g, f over 2. Okay? That means I apply this to a vector vw, that's f of v, g of w. You see, I symmetrize the form. I didn't want to get into this tensor calculus, but I will get into it later on. Okay, but I symmetrize the form by having fg plus gf, so I apply it to a vector f of v, g of w. So now what do I have to do? G of w, of v, f of w over 2.
So you need to define multiplication or you need to define multiplication of forms, otherwise it's...
The point is multiplication of functions. So, right? So, okay. The notation, let's say ds dt, say 2 d's, means, how do you apply that to a vector? It's the symmetric form applied to the vector. So it means ds applied to v, dt to w, plus dt to s, dt to the other way around divided by 2. You symmetrize the form, that's what it means. Okay? We will get into this. I think it's well worth getting into because nobody knows what we're talking about here. But, no, seriously, we need to get into this, right? When you see that symbol, that means the symmetric bilinear form. So this means the symmetric bilinear form for meter, and this means the alternating bilinear form. And so that means instead of applying FVGW plus GWFV and so on, you put a minus sign in the middle. Okay? There are two kinds of things. So this means here, just the norm of R, this is the norm of theta, this is the norm of phi. Okay? That's the notation. So we'll talk a lot about that tomorrow.